Today we're going to start chapter 3. Chapter 3 is probably my favorite chapter of this particular class. There's a couple of reasons for that. One is because I think that the book does a really good job of developing the whole chapter to be very cohesive, so they do a nice job with that. The other reason is because I feel like for the kids that this class is designed to help you learn to teach, it hits things really well. A lot of the same issues that you're going to see are going to come up in here. In particular, this chapter, not 3.1 specifically, but chapter 3 in general, talks a lot about ways of thinking about addition and subtraction, multiplication and division. And that's pretty much kindergarten through about 4th grade. And I know a lot of you, that's kind of where your heart is and who you want to be teaching. So I think you'll get a lot out of it. 3.1, that said, is a lot about history of where our numbers came from, how numbers have been thought of in the past. So everything I just said may not feel like it's very applicable to 3.1, but it tries to give you some historical perspective of where we've been and where we are now. Okay? All right. So we're going to get started today. Our section is titled Numeration Systems, and we're going to talk about different people's perspectives of numbers. And the first one that I'm going to mention is actually the Hindu-Arabic numeration system. And whether you knew it was called that or not, this is the system that we use today. It was developed by the Hindu, and it was transported to Europe by the Arabic. Some facts about the number system, things that I know that you know, you may not have thought about them in these ways. All of our numerals are constructed from 10 digits. Digits are a single number or numerical value. So when I talk about a digit, I'm talking about a single value. So 10 is not a numeral. 10 is two numerals, 1 and 0. So what are our 10 numerals? What do they start with? They actually start with 0, and they would go through 9. So that's why we have 10 of them, even though 10 itself is not a digit. Place value is based on powers of 10, right? So when we talk about the tens place, we talk about the hundreds place, it's because 100 is 10 squared. We talk about the thousands place, it's because 1,000 is 10 cubed. It's all powers of 10. And just a reminder about exponents is that, and this will come up a couple of other times in our chapter, when we multiply an exponent a to the n, this is a times itself n times. And we've already talked about this before, and I know you've seen it many times throughout your life, but just as a reminder about that. All right, so our first folks we're going to talk about are the Egyptians. So this is long ago and far away, like Bible times kind of stuff, right? The Egyptians. The Egyptians have several numerals, and their numerals are based on repeatedly writing the value over and over again. The first Egyptian numeral looks like our number 1. They call it a vertical staff, and it actually has the value of the number 1. So that's convenient for us, easy to remember. The heel bone kind of looks like the symbol that we've been using for intersection, doesn't it? Looks like that upside down U. And a heel bone has a value of 10. The next symbol almost looks like an incomplete 9. Yeah? It's called a scroll, and it has the value of 100. The lotus flower might be the most fun one to draw. Any guesses, now that we've looked at this pattern, as to what a lotus flower might be worth? 1,000 is it. After our lotus flower, we have what they would have called a pointing finger. I am not going to promise you that my images are amazing. They're adequate at best. So if you want to see better images, that's what Siri and Google are for. So maybe even Alexa could help you. I don't know. But somebody, your book has examples as well. The interesting thing to notice, too, is that just like if you were to look at my handwriting and Kayla's handwriting, they're not going to look the same. If you look at different versions of Egyptian script, like this, they're not actually all going to look the same either. So if you look on the internet for this and you're finding a figure that looks a little different, that's actually the why behind that. All right, so I think you know the answer, though, but what is a pointing finger worth? 10,000 is it? The next one should look something like a fish. Okay? Your book calls it a pollywog. I have taught out of other books that will call this a burbo fish. But it looks like something like a tadpole or a fish, and it has the value, of course, of 100,000. Our last one is an astonished man. I think he's astonished because he's worth $1 million. I mean, if I were worth $1 million, that'd be pretty amazing. You too, right, Erica? Yeah, absolutely. I want to show you just another version of the astonished man because I think this is a really good example of one that looks really different if you look in different historical resources. Another version of the astonished man looks like this. Can you see him? He's like sitting on his legs like knee style, right? Those are his knees. They're bent. That doesn't look anything like that other picture, right? It really doesn't. But kind of to give you some perspective that you don't always have exactly the same image. Okay, so let's talk about theirs. What they would do in their system is if they wanted to represent the number 5, they would write 5 vertical staffs. Okay? If they wanted to represent the number 90, they would write 9 heel bones. So they just repeatedly write a symbol for however many of them that they need. So when we're taking a look at this symbol right here, and I see 3 of this shape, it means I'm going to have 3 times whatever that shape is worth. Okay, so let's actually do the questions that's asked, but just as a perspective, I wanted to make sure I mentioned that first. This question says, what Egyptian numeral comes before this value? So it's asking the question in the order it really wants you to answer it. So we're going to start with that question, even though some of you are very tempted right now to just change this into our system and write down what the number is. We're going to get there. But what the question is actually wanting you to do is to take a look at the last value. What is that last value? 10. What would come before it? 9. So all of the beginning stuff stays the same. I have 3 scrolls. And then I would take my heel bone and I would turn it into what? 9 vertical staffs. What would come after this digit? This numeral, rather. Yeah, we would just take what we already originally had and we would add a vertical staff. So I have my 3 scrolls, I'll have my 1 heel bone, and then I'll have a single vertical staff afterwards. Now we're going to get to the question that y'all wanted to really start at, which is just to turn it into our number. If there are 3 scrolls, what are they worth? What's a single scroll worth? 100, so it's 3 scrolls worth. 300. So basically, I'm going to write it out just so that you can see it. They have 3 times 100, plus they have their heel bone, and what's their heel bone worth? 10. So this number is 310. And now we're going to do it in reverse. We're going to start with one of our numbers, and we're going to write it in their system. So this number is 23,145. So we're going to go digit by digit. What is the first digit? 20,000. Exactly. It's a 2 in the 10,000s place. So how do I get a 10,000 in their system? What does it look like? A pointing finger. So I need 2 pointing fingers. You got it. So do your best to draw 2 pointing fingers. They're going to look better than mine. I'm sure of it. The 3. What symbol am I going to use to represent the 3? It's a lotus flower, so I need 3 lotus flowers. Good. The 1, what do I need for that one? A scroll. The 4, 4 heel bones. And the 5. 5 staffs. So, pros and cons. What is something about this system that is a pro? It's easy to read. I agree. And it's easy at least maybe not efficient, but it's easy to write. Even if you're not an artist, because I told you that the symbols don't need to look like perfect, right? It's really not hard to write. So these are definitely pros. What's some cons? Time consuming, right? What happened if I gave you 99,999? You might all throw me in a ditch. I mean, like, really, right? Like, seriously, come on. Yeah, like, that's not going to be terribly efficient. And if we were doing like addition or subtraction in this system, it would become even more cumbersome, wouldn't it? Yeah, it really would. It would be very messy, okay? So these are our friends, the Egyptians. Now, what you didn't notice, because we'll notice it as we keep moving forward, is they're also sort of missing something. They don't have a zero. They don't have any way to write the number 0 in their system, and certainly not negatives and things like that. But the 0 is a problem, and it becomes more of a problem the more we get into this. In their system, it sort of doesn't feel that problematic, but as we move into the Babylonians, you're going to see that the 0 not being there is very problematic. So let's take a look at Babylonians. Our Babylonian friends only have 2 numerals. That's it. 2 numerals. One that looks like a triangle. I know you're tempted to call that an upside down triangle, but did you know that that's still just a triangle? Yeah, it is. If you want, when you're drawing these, I am totally cool with you not filling your triangles in, just for time-saving purposes. So if you make your triangles hollow, it's okay. The triangle symbol is actually worth 1. And the second symbol, which looks like sort of like an arrow or an arrowhead, if you want to, again, shortcut this to write it like a less than sign, just to mimic the outside image of it, I'm okay with that as well. And it has the value 10. Now, before I get to properties, if all you knew was that you had a 1 and a 10, and I gave you the number 900, this would be very unfriendly. Agreed? So they don't just have a 1 and a 10 and that's it. They actually have some other properties of their system. They have a system called a place value system, and like we have a place value system as well. For example, when I write the number 44, you recognize that these 4s mean something different. I mean, but they're both 4s, so when we talk to young children, that can be very confusing. I have my husband's, it's a short-tailed relative, we'll go with that. And he's in his 20s, he has Down syndrome, and he has a really difficult time understanding money, right? Much like a small child would. If you gave him 5 ones, he would definitely think that was worth more than 1 5. Okay? That's something that young children really have a difficult time with when they're first introduced to it. Coins are kind of the same way. I mean, how in the world is a dime worth more than a nickel? I mean, the nickel's like bigger. Like, what's the deal? Okay? So this idea of place value is really important. So in their system, they have a place value system as well. In our system, our place values are values of base 10. And theirs are values of base 60. So let's take a look at what I mean by that. Well, in our system, we have a 1's place, and then we have a 10's place right here, like this, right? Well, they don't have a 10's place, they have a 60's place. And then what would happen next, this is what happens when you don't actually use the right symbol to erase. Come on. Here we go. All right. Our next place value in our system would be the hundreds place, but it would be hundreds because it's 10 squared. That's why it's hundreds. It's all powers of 10. So we go up to 60 squared, and then we go up to 60 cubed and 60 to the 4th. It's all powers of 60. The biggest values in front, the smallest values at the end, just like we do. So what does that mean? Well, it means, for instance, if you had the value, we'll go with 62, that you would need 160, right? Like 1 right here. We'll write their symbols in a minute. And you'd need then 2 1s. I feel like it's when I go to the bank and I tell them what I want my denominations in, right? How many 1s and how many 10s and how many 5s do I want? It's like that. So I would have 160 and I would have 2 1s. Well, how do you write a 1 in their system? Well, you write it as a triangle. And how do you write a 2 in their system? Well, you write it as 2 triangles. And then sort of the way I've written it, there's this inherent space that's occurring in between here. And that's fine, but can you imagine that to be somewhat problematic when you're actually looking at this number? I mean, there's not like a comma to separate it. What happens if your space doesn't quite look big enough? Somebody might interpret this as the wrong value, right? So this place value thing can be very confusing. We're going to do an example with their number system. Now, I can tell you what I would like for you to do, all right? Anytime you see the value go from a larger value, I said it wrong, from a smaller value to a larger value, the system had to change places. So right here, well, let's just write it in for a moment. This is a 1, this is a 10, these are all 10s, right? And then these are all 1s. Everybody good with that so far? So I can't, just when I move from left to right, if the symbol goes from smaller to larger, the place value had to change. So there is for sure and certain a place value change right there. Because I don't see any spaces otherwise, I can assume that there is no other place value change. So I have 1's place right here. This is the 1's place. And this is the 60's place. That looks like 66. Let me try that again. Now it looks like 605. So sorry. S's and 5's are just terrible, terrible, terrible in math. Okay, so we've at least got, and what we have, our best assumption is 2 place values here. All right, let's answer the questions again as they were given, which have to do with numbers coming before and after. So if you are a Babylonian and you want to be able to write down that this person who previously owed you whatever this was amount of money now owes you $1 more, I'm sorry, $1 less, because it said before, what would I have to do to this symbol to show that it's 1 less than what I had before? Say it, Cassidy. Subtract 1 from it. Somebody said take away. Take away what? A triangle, right? 1 is a triangle here, so we're going to take away a triangle. So the triangle stays from the beginning. I had, it looks like 5 of the arrows. And then how many original triangles do I have other than that? Is it 9?
Yes.
Okay, so I only have 8 now. You're welcome for me letting you not fill triangles in right now. It's a lot of triangles, right? Okay, so taking away a triangle, taking 1 away. What about if you have to increase this number by 1? Okay, so we're going to write that down. So right here, there's 9 of them, and if I add 1 more to it and I have 10, I have a symbol for the number 10. It would be an arrow. But then if I add an arrow to the 5 arrows I already have, I have 60. This is like having a 10 in the 10's place. What happens when we get 10 and we're adding and we get 10 again? You have to go over to the next place over, right? You have to move on. So I would have, if you want to think of sort of progression of what I've done, I've started with this. Okay, so you can write it and just write it out. But there's 10 of them right here, right? And there's 5 of them right here. I'm just counting, and there's 1 of them right here. Well, 10 of these is worth 1 of the other symbols. So I can change this into one of these, like this. So now there's 6 of them here, and there's 1 of these here. Right? But 6 10s is the number 60, and in a base 60, I can't have a 60. Just like in a base 10, there's really not a numeral for 10, right? Anytime that happens, I have to move it over to the next symbol over. So this symbol at the beginning now needs to increase by 1, which looks an awful lot like this. Are you guys with me? This is the next symbol. And I hope that you've got a red flag going off in your head that says, that doesn't feel right. There's something weird going on. There you go. So that's my next question to you, part C. How else could the value you just found in part B be interpreted? 2. That's a problem, right? If you've written it in such a way that there looks like there's a little bit of space between it, it also could be thought of as 160 and 1 1, right? So that would be 61. So you could think of it, looking at it and thinking that's a 61. So this is one option. This is one option. We actually meant it as two 60s. That's what we meant it as. So we were intending it to be the number 120. And I hope you're not an accountant in the Babylonian era. How are you supposed to keep track of which one's which? It's not good. So our value that we were supposed to be getting in our system was supposed to be 120. What was the original value that we had? Well, it was 160. Yeah. And then I had 6 tens and was it 9, right? Ones, not 6 tens, it was 5 tens, my bad. 5 tens and 9 ones, and it was the number 119, right? That was our original number we started with. This value should have said the original value. Our number was 119. That was what it was. So 120 should have been the number that came after it. But there's no way to distinguish 120 from 2. Obviously a problem. And the reason it's a problem is because we don't have a placeholder for 0. If I had a 0 I could plug in there, right? We'd be good to go. I mean, that's the reason that you know that 20 means 2 tens as opposed to just being 2, right? It's because we have a 0 and they didn't. All right, we're going to go the other direction now. We're going to take one of their, our numbers, excuse me, and we're going to write it in Babylonian. Okay. So how do you do that? Well, I'm going to show you a process, and this is not the only time I'm going to show you this, so don't freak out when you're like, what in the world did she do? Because it's kind of a funny-looking process, and we're going to do it several times throughout this section with different number systems. So what we're going to do first is we're going to figure out what the place values are worth in their system. We have the ones place, we have the 60s place, so that's all good. The next one is 60 squared. What is 60 squared? $60 times 60. Thank you. It's 3,600. Our next value would be 60 cubed. What would that one be? Yeah, 216,000. And we could do 60 to the 4th and 60 to the 5th. We don't need them. And the reason we don't is because our number that we're dealing with is already smaller than the 216,000 that I just came up with, okay? So when I'm all said and done with this, I don't need that column because 216,000 is more than I have, but I will need the other 3. We're going to do what I call a division algorithm. We're going to take that highest place value, which is 3,600, and we're going to write it outside of a division. And you'll notice my division has a line underneath the 3,600. There's nothing really special about that. It's going to look like a top hat here in a minute. What we're trying to divide is the number we were given, which was 43,205. And I'm going to extend this to make it look like a top hat. And what I want to do is I want to do the division. And your calculator is great, so I hope you have it with you today. And I want to know how many whole times does it go in. Okay, I don't want a decimal. I just want to know how many whole times does it go in first. How many times will 3,600 go into 43,205? It's 12. Okay, and then find out what is 12 times 3,600. 43,200. So that's almost everything, isn't it? So if I subtract, what does that give me? 5. There's no skipping divisions, okay? Wherever we start, we're going to divide by all of the values that come below. So I know it feels weird to do what I'm about to do, but we're going to write divided by 60. And we're going to recognize that that means it goes in 0 times. And 0 times 60 is 0. And we're going to do the subtraction even though you're rolling your eyes and thinking, seriously, why did I write that part down? Okay? And for the purposes of what I'm doing right now, it's not real obvious, but it will be when we get toward the end of this section with some of the other systems, okay? So for right now, just humor me, write down the 0. okay? Our last thing that we divide by is always 1. So obviously 5 will go into 1 5 times. I said that backwards. 1 will go into 5 times. 5 times 1 is 5, and I end up with a remainder of 0. So I should always end with a remainder of 0 after having divided by 1. Okay? So what does this mean? Well, it means that I have a 3-digit number, okay, in their system. We'll fill it in with their digits in a minute. That has a 12, a 0, and a 5 here. Okay, that's what I found, written sort of horizontally instead of vertically. We're going to start with the 12. How do we write a 12 in Babylonian? Yeah, an arrow and 2 triangles. How do we write a 0? We don't. We can leave a space there. That's fine, but it still doesn't really mean that there's a 0 there. It just means I changed place value. How do I write a 5 in Babylonian? 5 triangles. So at best, this right here is what I get for the number 43,205. And there's absolutely nothing that tells me that this is really 12 3,600s, 0 60s, and 5 1s. It would actually look exactly the same if it were 12 60s and 5 1s, wouldn't it? Because that space will tell me it changed places, but it doesn't tell me that there's a missing place number in there. There's nothing that does that. It actually would also be true that it would look the same if I had 12 times 3,600 and 5 times 60. And if I'm not being careful on spaces, I actually might think that this is the number 17. Like if they were run together a little bit closer and I just counted up what was there, there's a 10 and there's 7 1s. Obviously a problem, right? There's definitely problems with this. All right, our next friends that we're going to talk about are the Mayans. The Mayans have 3 numerals. They have some very different things associated with them. They have 3 numerals. Their first numeral is a dot, and it has the value 1. Their second numeral is actually a horizontal line or line segment kind of symbol, and it has the value 5. And their third symbol is like a shell. That's how they sort of think about it. It's a shell. And lo and behold, they were the ones who said, we should have a number 0. And they did. Now, it addresses some of the problems that can come up, but we'll see very quickly it doesn't address them all. Okay? So I've got 1s, 5s, and 0s. They have a place value system as well. It's a base 20 system. So let me just talk about what base 20 is, and then I'll talk about how they modified it and why. So a base 20 system, like we have a base 10 system where we have 1, 10, 10 squared, and so on, right? 10 cubed, 10 to the 4th. We looked at the Babylonians. They had 60s. Everywhere we have 10s. Well, if we actually had a numeral system that was base 20, it would be a 1, a 20, 20 squared, 20 cubed, and so on. That's what an actual base 20 system would be. They don't have that. They have a modified base 20 system. So what does their system look like? How is it different? Well, it has the 1s place and the 20s place. That part's good. But in their third placeholder, they don't have 20 squared. They have 20 times 18. And after that, they square the 20, and it's still times 18. And then they cube the 20, and it's still times 18, and so forth. Okay? So they continue afterwards as though they've got powers of 20 going on. But there's this really weird 18 that shows up in the middle here. And I want to talk just briefly about why. So somebody's going to find out for me real quick. What's 20 times 18? It is 360. They liked 360. Any guesses as to why? What's that? Yeah, it was the calendar year. And we know that that's not exactly right, but it was awfully close, especially at this point in time. 360 days in a year. That's why they wanted it. Why do you think they used a base 20 system? Why do you think we use a base 10 system? That's not why. You can easily get to 100, but that's not why. How many fingers do you have? You have 10. I mean, like, not joking. That's why we use a base 10 system. If you had been born, and we had all been born, with 8 fingers, we would be in base 8. Like, that's the deal. We have 10 fingers, and that's why we use base 10. So why do you think the Mayans use base 20? They do, because they wouldn't have had closed-toe shoes like we do, right? Yeah, they would have been using fingers and toes. Now, there's something else about their system that's sort of unfortunate, because I've led you to believe, even in the way I wrote down my numerals, that this is not true. But number 3, you'll see, is that they write their numbers vertically. So what does that mean? Well, what it really means is that over here, where I was writing out for you their system, they actually have the ones place, and then they have the 20s place, and then they have the 20 times 18s place, and then they have the 20 squared times 18, and so forth all the way up. Lowest number at the bottom, highest number at the top. If you have a dot and a bar in a place value system, like for example, if you had the number 6, you would have a dot and you would have it over the bar. So if there's dots and bars present within one place value system, the dots are always on top. Okay? So that's about it. Let's take a look at a couple of examples in their system. Okay, so we're not trying first to figure out what this numeral is, but I do need to talk to you about how you go about dividing between place values. I said just a moment ago that dots are always on top of bars, right? So if you ever see a bar on top of a dot, it means the place value changed. So there's a place value change where I drew that pink line. So what is the value below? Well, it's the smallest value of our number, just like our smallest value is always on the right-hand side of our number, right? The ones place. The bottom number is their ones place. So how many ones do they have? They have 9, right? A 5 and then 4 ones. Are we good with that? A 5 and the 4 ones, so there's 9 as their first place value. So if you wanted the number that came before this, the only thing that's going to change is the ones place. What would come before 4 dots and a line? 3 dots and a line. So the stuff on top stays the same. It was 2 dots and a line. None of that changed. And the bottom part changes from 4 dots to 3 dots and a line. This is the number that would come before the one we were given. What's going to happen if we try to find the number that comes after? We get 5 dots, which is a line. Good job. So here's the problem with that. If I have 2 dots in the line, because I didn't change my top value, and then I have 2 lines, which is now my bottom value, what's the problem? How do you know where the place value changes? Right? Like I told you when we started with the number that I at least knew there was a place value change where I drew the pink line, because there were bars above dots. Well, now there's not any bars above dots. I just have lots of bars at the end. So the problem is that this number that we just found in part B could also be interpreted as the number 17. Because each of my bars is worth 5, and the dots is worth 2. It could be interpreted as a 17. It also could be interpreted, this is the most awkward, I will often have students want to interpret it this way. It could also be interpreted as 2, because there's 2 dots, and then there's one, sorry, not a 1, a 5. I'll fill in the place values in a minute. And then I have another 5. So each symbol is different, and I have another 5. Okay? So if I interpret each of these as separate values, so this is 2, whoops, that's not a good color. This is 2, this is 5, this is 5, and this is 5. I mean, like, it could be that those are 4 independent numbers. It's possible. So I've got a 5 in the ones place. I've got a 5 in the 20s place. I've got a 5 in the 20 times 18s place. and I've got a 5 in the 20 times 18 squared place. That's a way bigger number than 17, and also way bigger than the number I should have been getting anyway before. So it could be that 17 is the number it's interpreted as. It could be that, I've got this one written down, I didn't think I did, that it's 16,305, that that's the number that we're actually looking at. And again, obviously, 17 and 16,000 are quite different. So that's a problem. Erica.
So when you're writing those, it's 17, or it's 20 times 18 then to the power of, right? It's not 20 squared times 18.
I wrote it wrong. I'm sorry. Thank you for fixing that.
Okay,
yeah, the squared should have gone on the 20.
Okay.
It is. Please fix that. Thank you, Erica. It should say 20 squared. Yep. Good fix. Good eye. All right. So yay for the Mayans giving us a 0. We haven't actually seen the 0 useful at this point, but it is useful. But there's still problems. We just found one. Let's take a look at what happens when we take the actual value we were given with our 2 place values that we assume are there, because that's the best assumption. It's the most natural assumption. So at a 9 below my pink line, what's above my pink line? 7. So the natural assumption is that the original value, this means original, the original value was 7 in the 20s place and 9 in the 1s place. That's the assumption that we probably, not probably, that we would have made when we first started. What is this value? $100 what? 149. Yep. 149 was the number that we had initially started with. So our number that we tried to get over here was actually the number 150. That's what it was, because it was the number that came after. But the problem, of course, is that 150 looked a lot like 17, and it could also even be 16,305. Not good. All right, so let's take one of our numbers now and write it in their system. The number we're going to deal with is 58,532. And when we did this with the Babylonians, that's when we just did, what I mentioned to you is we need to know what the place values are all worth. So they have, the 1's place, and then they have the 20's place. And then we had 18 times 20, which we recognized and said already that was 360. And just like with geometric series, we just multiply by the 20 every time from there. So if I take 360, and I multiply by 20, what do I get for my next place value? 7,200, and then times 20 again, 144,000, and that's bigger than the number I'm working with, right? So I don't really need this value. 7,200 is a big enough value. So I start with the biggest place value that divides my number, that's 7,200, and I write it on the outside. And I write the number I was given, 58,532, underneath. And I ask, how many times will 7,200 go into 58,532? How many whole number times? 8. What is 8 times 7,200? Good job. And if I subtract, what do we get? Nice, 932. Okay, my next place value was 360. So how many times will 360 go into 932? 2 times, and 2 times 360 is 720. Very good. And if I subtract, 212. And then I'm going to divide by 20, next place value. How many times will 20 go into 212? 10. That's 200. Leaving me with 12. My last value to divide by is the 1's place. And 1 will go into 12 times. When I subtract, I get 0. So I'm done because I divided by 1, and I have the remainder of 0. So the numbers I just got would be 8, 2, 10, 12. How do I write an 8 in Mayan? Right, a bar and 3 dots on top. How do I write a 2 in Mayan? 2 dots. How do I write a 10 in Mayan? 2 bars. How do I write a 12 in Mayan? 2 bars on top of 2 dots. I said that wrong. 2 dots on top of 2 bars. Let's get that right. That's the right symbols. But can you see how that could be interpreted incorrectly as well? Yeah, because those 2 dots that represent the number 2 could very easily be assumed to go with the 2 bars before. It's very easy to think that this is the number 8, this is the number 12, and this is the number 12. It's not cool, right? So there are reasons why we don't still use some of these systems today. All right, I have one assignment for you to do for next time. This is super simple, easy assignment. Our next system that we're going to look at are the Roman numeral systems. The Roman numeral systems are everywhere. You see them used. So give me a couple examples and we'll wrap it up. Where do you see Roman numerals used today?
Like formal outlines, yeah.
Outlines, and sometimes also in books, like chapter headers for books. Where else? Clocks is a really good one. You'll often see it for sporting events that occur in multiples, like we're in the middle of the Olympics. There's probably a numeral that they're showing in, and I haven't seen much of the Olympics. The Super Bowl, that's another one. Yep. So you'll see it in a lot of places. Here's your assignment. I want you to tell me when you come back in. You can read a little ahead if you want, but take a picture of it, study it, think about it. There's something wrong with the clock on Rayleigh Chapel. And your assignment is to try and look at that clock and figure out what's wrong. Okay?